Hi, this is Physics 1C for November 19th. Tonight we're going to be talking about resonance and AC circuits, as indicated by this graph right here, and then we're going to talk about transformers, and we're going to do a couple of problems to help you out with your homework a little bit. All right, so let's get started. So we talked last time about AC circuits, and the type of AC circuit that we talked about, just to kind of run back through it, was one in which you had a voltage source that looked something like this in the circuit diagram, connected up in series to an inductor, a capacitor, and a resistor, like that. And we learned about some quantities that you can understand from this thing. So, for example, we learned about the relationship between the voltage and the current, which is done through something called the impedance, which is represented by Z. And Z is something that is equal to this. Where the XL and XC are related to the inductance and the capacitance within the circuit. So X sub L is equal to the frequency in the circuit times L, and X sub C is equal to the 1 over the frequency in the circuit times C. So we want to talk about resonance, which is a phenomenon that occurs when a system is tuned very close to what's called the resonant frequency. And the resonant frequency is associated with these two terms right here, with XL and XC. So one thing you can notice is if you plot, or if you rewrite this equation right here, is that if we write it like this, V over Z is equal to I. And we replace for Z a much kind of bigger equation here. So if we write it out in the full form, then what we would have is omega L minus 1 over omega C whole squared, like this. And that would be equal to the current. And now it turns out that if you plot this current as a function of omega, so if you treat your voltage and your resistance as constants, and there's 3 different curves of this function plotted over here to the left. It gives you the values of the circuit elements here. What ends up happening is that you get this very sharp peak. And where that peak occurs, you can probably guess by looking at this equation right here. The place where you're going to get the maximum value of your current, and you could determine this by using algebra, by using calculus if you want to. You can maximize this function, but if you just think about what it is, it's a simple ratio. You've got a voltage divided by something, which is kind of a fixed value of resistance, and then you have this term right here. And as a function of omega, the place where the right side is going to be the biggest is the place where the whole denominator gets the smallest. Yeah, the denominator gets smaller, exactly as Ash is saying. And the only way that can happen is if this term right here drops to 0. Okay? Any given circuit is going to have some kind of resistance in it. So obviously by making the resistance smaller, you can get a bigger peak. And that's indicated by the fact that there's 3 different curves here. One's 2,000 ohms, one's 500 ohms, one's 200 ohms. Obviously the 200 is going to have a bigger peak than the other two by comparison. But they're all peaked at exactly the same value of 1,000 omega, 1,000 angular frequency, right? And you can kind of figure it out from these numbers here. But you might remember that when we discussed circuits that just have inductors and capacitors in them, there was this type of frequency that always showed up, and the exact same thing happens here. So what we want to do is we want to set this equal to 0. So you end up getting omega L minus 1 over omega C is equal to 0. And then if you solve this for omega by moving the 1 over omega C to this side, and then just multiplying omega and dividing by L, then you get the exact same relationship that we got when we talked about LC circuits. This is called the resonant frequency. Resonant. I was going to write resonant or natural, because it could also be referred to as the natural frequency. And one kind of applications of this is that if you have a signal that you want to send, like a radio signal, for example, let me not jump ahead. You might notice that this particular problem that L and C are given, and if you plug those in, you do 1 over L, which is 2 henries, and you multiply that times 0.5 times 10 to the negative 6 farads, and then you square root this whole thing, Then 2 times 0.5 is obviously just 1. 1 over 10 to the negative 6 is going to be 10 to the 6. You square root, you're going to get 1,000, basically. Radians per second. Which is what the peak occurs here at. So what you can do with this, as we'll kind of learn more about in the next chapter, but I already hinted at, a guy named Hertz figured out that you can send waves through the air using electrical circuits, according to Maxwell's equations. And when you're producing these type of signals, the signal that you produce is also related to the inductance and capacitance of a circuit. And so what you can do is you can basically tune into that signal by constructing another circuit that has a similar resonant frequency. So you basically would have a transmitter, and you'd have a receiver, right? So here's your receiver, like your television set or your radio, or the Wi-Fi. The best example for you is probably the Wi-Fi radio in your phone, for example. So this could be like your phone, could be the receiver, and the transmitter could be like your router, your Wi-Fi router, right? And the idea is that if you want your phone to be able to connect to your Wi-Fi router, you have to have it scan, right, and see what available networks there are in the area. And then you have to look for the one that's yours, or, you know, if you're at a Starbucks, the Starbucks, or if you're at a library, it'd be the library's Wi-Fi, or if you're on campus, and you tune into it. Now, you don't see that tuning occur because on your phone, there's just a name associated with the wireless network, right? But on like a radio in your car, if you tune that radio, you tune into a specific frequency. And the idea is that the transmitting frequency, so there's a frequency that comes out from the transmitter, just needs to be synced up to the receiver here. So basically within the receiver, there's either adjustable inductors or adjustable capacitors that allow you to modulate and change this frequency. And as long as this right here has the same natural frequency, or the same omega, this is sometimes called omega naught. If you transmit at a certain frequency, then you receive at that same frequency, then the kind of impact of this is that the current in your circuit is going to be really big when you're near this point, right? That's the idea, is that this receiver is going to drive kind of electrons within your circuit here, and the current that they feel is going to be greatest when you're really close to that natural frequency, basically, where you get this big peak right here. And this is how your phone can distinguish between other Wi-Fi signals that are carried on a very close number. Now, numbers for Wi-Fi, I don't know off the top of my head, but as an example of this, on like the FM radio dial, right? So if you have like a station like at 106.7 megahertz, so this is like K-Rock, you could have another station that is like 1 point higher on the dial. They usually, in FM radio, they always separate them out in terms of these odd decimals, right? There's no 106.8, although in principle you could tune into it. The idea is that when you're tuned just into this one, you hear just that station because you get this big peak in the intensity of what you're hearing, right? But then when you tune into this station, you get a different peak, right? And as long as those peaks don't have too much overlap, then you can distinctly and clearly hear this radio station. However, if you're traveling between cities and two different cities have radio stations that might be really close together in terms of their frequency, then you might get kind of an overlap. So if you're driving between here and San Diego, you might hear two radio stations at the same time, right? Okay, there's some questions here. So Wi-Fi are not transmitted at the same frequency. There's a range. Yeah, and then Miara's actually already answered the question. Miara said there's a range from 2.4 gigahertz to 5 gigahertz, which is the standard, but there's an acceptable range above and below these frequencies. That's right. And so the cool thing about this is you hear about the airwaves, you hear about bandwidth and all these things. The cool thing about this is that all of these signals can be sent out all at the same time. And the way that it ends up working is because of the fact that there's this resonant frequency and this gigantic peak that occurs, it's really easy to distinguish between another station that might be transmitting at another peak, basically, right? So that these two are kind of indistinguishable from each other. It's actually really similar to optics in a weird way. We're talking about like distinguishing between two stars in the sky. Regardless, kind of getting off track here, the point is that this can be exploited and it can be used to tune in to radio stations, and it's how we're able to have all this information that's kind of flying around us all the time. And if we want to key in on one portion of it, one channel of it, it's easy to do just by using this concept of resonant frequency. There's a lot of concepts in physics that are associated with resonance. This is just one of them, and it's pretty interesting. It allows us to make radios, and it also explains how Wi-Fi radios work, which is another version of the same thing. Okay, any questions before we go on to this problem? Sorry, I shouldn't have gone ahead. I'm recording lecture. Yeah. This little button down here is red. That's how you know I'm recording it. Okay. If there's no other questions about the content, then I'll go ahead and keep going. I appreciate you asking that, though, because it's really easy for me to forget to turn something like that on, but it's on. Okay. So here's an example of a problem we can do with this. We're going to do two problems. This first one should be pretty short, but the next one, I don't really know how long it's going to take. All right. So you have a series circuit set up like this. You've got a resistor, an inductor, and a capacitor connected to an AC voltage. There's a couple of pieces in here. There's an ammeter right here. There's a voltmeter right here, and then there's 1, 2, 3, 4. There's 5 or 4 more voltmeters up here connected between different pieces of the circuit. You're kind of given the voltages at certain points in time. So it says, similar to some radio tuning circuits, it's connected to a variable frequency AC source with an RMS voltage of 1 volt. Let's write that down, VRMS. Is 1 volt. We want to find the resonant frequency, and at the resonant frequency, we want to find the inductive reactance, the capacitive reactance, the RMS current, and the RMS voltage across each element. Okay, so let's go through and do this. Part A says to find the resonant frequency. Okay, so as we said above, that resonant frequency is 1 over the square root of L times C. And in this case, we're given the inductance is 0.4 millihenries, so 0.4 times 10 to the negative 3 henries, multiplied by C is 100 picofarads, so that's 100 times 10 to the minus 12 farads. We need to square root that. What's that equal to? Can you all calculate? Grab my phone. So I get like 1.58. Any questions about that? Do you guys get the same thing? Do y'all get the same thing? Okay, great. X of L is the next question, the inductive reactance. To get that, we just do omega times L. So we would get the thing we just got, 1.58 times 10 to the 6th radians per second, multiplied by the inductance, which was 0.4 times 10 to the minus 3 henries. Let's see what that is. So that times 0.4 times 10 to the minus 3. I get 632. Ohms, because it's inductive reactance. Okay, we're going to calculate X sub C as well, which is 1 over omega C. What do we expect to get? What should XC be equal to in this case? Do we know in advance what we're expecting to get here? Remember the whole idea of what resonance frequency is that it makes this quantity equal to 0, which means that it technically makes this quantity equal to 0. We just calculated x sub L, so what does x sub C have to be? The same, exactly. Not 0, but they should be the same. Alright, so let's check. So we do this times I got the same thing, but off by a little bit. What did I do wrong? Let me try this again. I got 6,000. What did y'all get? I must have done something wrong here and I can't see it. Yeah, I got 6,325 too. I wonder if I did something wrong here. Let me start again. So let's see. 1 divided by... .58 times 10 to the 6th. This looks right. And if I take that number and I multiply by... Oh, no. I made a mistake. I can see what I did. This should have been 5 million. Right here. Yeah, this is kind of hard to read, isn't it, right here? So I'll just put it in a different color and indicate what I was... That should be -3, not -2. And then the answer you get then, here that's different, is 5 million. So, is it 5 million? Yeah. 5 times 10 to the 6th radians per second. And then that's going to give us here, this one's going to be different. And this will be different because the unit's the same. So this is going to be 5 times 10 to the 6th. This is going to be 5 times 10 to the 6th. It's nice knowing what you want to get as an answer because it'll help you realize that you made a mistake in previous parts, right? So this ends up becoming someone saying 2,000. That seems right to me because this is 2 over 5. Yeah, 2,000. So this is going to be 2,000 ohms. And my guess is this also gives us 2. Yeah, it should be easy to figure this out because this is 10 to the 6 to the -12. That gives us 10 to the -6 times 500, which is like 5 times 10 to the -4, which will be 2,000, I think. Let's see. $2,000. All right, so we get the same answer for both of these, which is good. Okay. Next. Any questions about that? This was still part B. So part C says to find the RMS current, IRMS. To calculate that, we already know VRMS, and IRMS is equal to the RMS voltage divided by the impedance. So this is going to be, we didn't calculate the impedance, did we? That was supposed to be the last part. So let's do that first. Let's calculate the impedance first, and then we'll do this. All right, so the impedance is going to be equal to the square root of the resistance squared plus XL minus XC squared. So this is going to be basically just equal to the resistance now, because XL and XC are the same. So the resistance of the circuit was 500, so we're just going to get 500 ohms equals Z. At resonance, the impedance is just equal to the resistance. Part C, we want to find IRMS, and we do that by taking the RMS and you divide by Z. So the RMS was 1 volt, is that right? Yep, 1 volt. And we divide that by 500 ohms. So we'll end up getting something like 0.002 amps. Someone else is saying the same thing in chat, which is good. And then the RMS voltage across each circuit element. Okay, so to do this, we just box this like this. For part D, to find the RMS voltage across the resistor, VR is equal to just our kind of Ohm's law equation. You just take IRMS, and you multiply by the resistance. This is going to give us it's basically the inversion of what we just did, so the answer we're going to get here is 1 volt. If we want to do the RMS voltage across the capacitor, we take IRMS and we multiply by X sub C. So that's going to be equal to 0.002 amps multiplied by 2,000 ohms. What's that going to be? 3 decimal places, and then we multiply by 2, so 4. And this is also going to be the same thing that you get if you do V sub L, which is just going to be IRMS times XL, because they're the same. XL and XC are the same. And there we go. Pretty straightforward. Anyone have any questions? All right, so most of these problems you're going to find to be pretty simple. This one is a little trickier, and I had to pull this from your textbook. There's no, example problem in the text that's like this, but this shows up on your lab manual problems. One of your lab manual problems is like the one that we're about to do here, and I think it's not exactly obvious how to approach it unless you've kind of seen something similar. So we're going to try to go through this. All right, so I kind of want y'all to take some time to think about the problem first. So I want you to take 5 minutes and just try to set it up. I could at least, set up a little bit of it. So we've got an Lrc series circuit, so just the same setup that we've had before. You've got a capacitor, an inductor, a resistor, so R, L, and C, all connected up in series with one another, and those are connected up to a 120 volts AC voltage, and that's the RMS voltage. So what we know in this problem is that VRMS is equal to 120 volts. We know that it draws 220 watts. I think that's most likely the average power, because as we learned last time, with the power kind of oscillates, so it's more likely that any power that they give you is going to be the average power that it draws. We also are given the power factor. I don't know what to call this, but we also know that this is equal to the cosine of what's called the phase angle, and in this case it's equal to 0.56. We learned some relationships for the phase angle last time. I could write them up here, for example, that cosine phi was equal to resistance divided by impedance, and the other equation we got was that the tangent of phi was equal to XL minus XC divided by the resistance. We also know that they tell us that the source voltage leads the current. Now that's a hint about something that's going on in the system. This means the current is kind of lagging behind the voltage. So the question is to find what is the net resistance R of the circuit, and then we want to find the capacitance of the series capacitor that will result in a power factor of unity when added to the original circuit, and what power will then be drawn from the line. So this is a little bit confusing what they're saying here. But with part B, what they're saying is, what kind of capacitor could we add to the circuit so that the new circuit would look something like this? We'd have a new capacitor. I'm going to call it C prime. There's really two options, actually. This is one option. What would be another option? Maybe that question's not obvious. Oh, no, it says series capacitor. Okay, it has to be this way. Okay, I was going to say you could also add a capacitor, in parallel like this if you wanted to, but I guess it has to be a series capacitor. So part A asks to find the resistance. Part B wants you to calculate the value of C prime such that cos phi becomes 0, becomes 1. Basically phi goes to 0. And then so on and so forth. So that's kind of the question. Don't worry about part C, because once we get part B, we'll be able to solve for part C anyway, okay? So take about 5 minutes or so and just see what you can solve here. And I really just want you to kind of get an idea for the difficulty level of the problem. So take 5, try to solve this. Anyone have any questions before I give you time? All right, go for it. I'll check back in at like 6:35. And I'm still here if you have questions. Feel free to type them or ask them. One. Unity means 1. Unless we're talking about some kind of unity among sports fans or politicians or something. No, I mean, in mathematics, unity always means 1 as far as I know, yeah. It comes from the idea that, any kind of counting system has to have a unit. And that unit could be like an inch or a foot or something. But there's always like the smallest possible unit, right? And that unit would have unity, basically. The property of being the unit, so to speak. It's definitely an archaic usage, I think. For sure. I understand why it might not be something you're familiar with. So, have you all been able to figure out what the resistance is yet? That was 7 minutes. I know it's hard, so if you haven't, that's okay. I just wondered if anybody figured it out yet. Even if you think you're wrong, it's okay to just kind of take a stab, if you know. Are you able to use E equals IR here? Maybe. I could see a way in which you might use it, yeah. Yeah, that's a good idea. Yeah, use the power average to find the resistance. Need to find IRMS, yeah, that's right. Yeah. So we've got this equation here that tells us that average power is related to IRMS times VRMS times cosine phi. And we have a lot of this stuff. We're given the average power, we're given VRMS, and we're given cos phi. So a natural thing to do from this is just to go ahead and figure out what IRMS is. So let's start with that. So for part A, let's say that IRMS is going to be equal to the average power divided by VRMS times the cosine of phi. Then average power is equal to 220 watts divided by VRMS, which is 120 volts, multiplied by the power factor, cosine phi, which is 0.56. Okay, so I get 3.274. Carry it up to that many digits. Amps. Do you want to agree with that statement? That that's the RMS current? Okay, that's going to be useful to us, so I'm just going to write that down, because now we can use this to find two things now. What can we use it to find? What do you recommend we use it to find? We can find R, right? Which equation can we use to find R? Okay, there's another power average equation. And well, if we substitute in the cosine phi with R over Z, we're going to run into a problem because Z is equal to unknown right now. So instead what we can do is there's another definition of average power that was I squared RMS multiplied by the resistance. So we can use that to solve for R. So we take the power that was given, which is 220 watts, and then divide by RMS, which is 3.274 amps. No, that's not that equation that you wrote down, Mr. Meowers. That's the voltage across the resistor. It's not the same thing as the voltage across, like, the VRMS of the circuit. Yeah, exactly. You would need to know the voltage across the resistor, and that's not given. All right, so 220 watts divided by that squared. Okay. Oh no. No. Okay. I kept a few more digits here, but I got 20.53. Yeah, I agree with that. So that's our resistance. 20.53 ohms. That's part A. Can we use the information we have now to find anything else that might be of use to us at some point? Z, yep, exactly. So cosine phi is equal to R over Z, which means that Z is equal to R divided by cosine phi. So let's just calculate that, because it's a handy thing to have to know what the impedance of the circuit is. We might need it later. Maybe not, I don't know, but let's just calculate it while we can. So 20.53 ohms divided by cosine phi, which is 0.56. I'm keeping kind of more digits on all these calculations when I plug them in my calculator, so if you start getting like a little bit off, like let me know. I got 36.65 ohms for this one. Not 6665. Okay, so that's our Z. I'm not going to circle it. It wasn't one of the things we needed to find. Okay, that's equal to Z. All right, part B. This is the part where it gets a little tricky. We'll need some of these equations up here. All right, so part B says, find the capacitance of the series capacitor that will result in a power factor of unity when it's added to the original circuit. Okay. What does it mean if the power factor is unity? What do we know then? What does that mean? Yeah, it means R over Z is equal to 1, right? So that R is equal to Z. It tells us something about theta too, phi or whatever. I'm sorry, not theta, but phi. Phi would be equal to 0 then, right? Because the cosine of 0 is 1. So how are we going to figure this out? How do we understand what this means? What's the capacitance of the series capacitor? How can I add, what would the value of a capacitor be here? And how would I figure it out? We don't know what this one is. We don't know what the inductance is either, actually. Ashley, should we combine them with 1 over C plus 1 over C prime is equal to -1? Sure. And then we could probably use tan phi as well. Yeah, there you go. All right, so first of all, this is a circuit where the source voltage leads the current, right? What does that mean about the relationship between XL and XC if the source voltage leads the current? If you kind of look back what we did last time. XL is greater than XC, that's exactly right. So we know that XL is greater than XC currently. And in order for cosine phi to be equal to 1, that means R equals to Z, and R is only equal to Z if XL and XC are equal to each other, right? So basically, we just need to make XC bigger. We just need to make XC bigger here, right? So currently, we have tan phi being equal to XL minus XC. That's the current situation, divided by R. And we'd like to basically change this so that tan phi, well, what would phi be in this case? If phi is 0, the tangent of phi is, what? We'll call it tan phi prime. If phi is 0, what's the tangent of that? It's 0, right? And so that would end up being equal to something like XL minus... Now in here, we're going to do exactly what you said, Ash, except I'm just going to point something out here. If I add a... if I add a resistor, or sorry, a capacitor in series, then the inductive capacitance is going to add just like this. And to see why X of C is equal to 1 over omega C, right? And if we did the equivalent capacitance here, CEQ, we would be doing exactly what you said in the chat, which would be 1 over C plus 1 over C prime, and then, raising that to the -1 power, right? And that would give us the equivalent capacitance, right? Well, because of the way that, XC is written here, right, then it turns out that you could basically just add them, just like this, when we put it in series. Because it's already inverses, right? To see that better, I guess it might be easier to write this in the following sense. So this whole thing would be equal to 1 over the equivalent capacitance. And if we multiply both sides by, let's see here, by omega, so if I throw an omega in here, then what we get is basically xc plus xc prime is equal to xc equivalent, right? Okay. All right, so that means that we can basically just use this equation that we've just written here, this one right here. This is accurate now, right? We know that as long as we make this thing bigger, it's going to make it so that this is equal to 0. Well, if this is equal to 0, that must mean the following is true, that xl minus xc plus xc prime is 0. We can factor this all through here, and we'll get xl minus xc. Distribute, I shouldn't say factor. Distribute that through. And then we don't know what this is, but, well, actually, we can actually calculate this. We're going to add this to the right-hand side, so we'll get xl minus xc is equal to xc prime. And that might not be super immediately obvious that that's going to be helpful, but we do know that in this first equation that we had over here, so we'll do this on a kind of separate equation line here, that r times the tangent of phi is equal to xl minus xc, right? So then we just use this equation. That means that r tan phi has to be equal to xc prime, which we can use ultimately to figure out what our capacitance is. Our goal here is to find out what the capacitor is, but if we know this, then we can solve for this. All we need to know is what tan phi is. But tan phi, we can figure out because we knew what cosine phi was originally, right? We can use this equation to solve for phi and then figure out what the tangent of that angle is. So let's do that. So if the power factor, cosine phi, is equal to 0.56, then phi is equal to the arc cosine of that. Which is 0.9764 radians. And we calculated R in a previous portion, right? R was equal to, just slightly up here, 20.53 ohms. So we'll have 20.53 ohms multiplied by the tangent of phi, so the tangent of 0.9764 radians. And that's going to be equal to xc prime. We'll just solve for xc prime first and make sure it makes some kind of reasonable sense to us, and then we'll solve for the actual capacitance afterwards. So we do 20.53, and we multiply by the tangent of 0.9764. It's kind of a math-heavy problem, but it's kind of the point of doing it. I got 30.37. Do you all agree? Oh, it went away. 30.37. You all agree? Okay. All right. And then this is equal to 1 over omega c prime. So continuing through, we get that c prime is going to be equal to 1 divided by omega times 30.37. And in the problem, omega was 2 pi times 50. Be careful, when they give you the frequency in hertz, you have to multiply by 2 phi. And then multiply by, not that one. There we go. And again, I wrote this down while you all were working, but they tell us that it's a 50 hertz AC line, so the frequency is 50 hertz, which is F, but the angular frequency is 2 pi F. Okay, so we get that. I got 5.24 times 10 to the minus 3. Assuming I didn't make any mistakes, which I easily could have here. There's a lot of calculations. Easily could have made a mistake there. Any questions? Do y'all get the same answer? Okay, let me do it again. You got something different. I easily could have made that made a mistake. 1 divided 2 divided pi. Then divided by 30.37. No, that's what I got. Anybody else get the same thing? Maybe there's some numbers here that are hard to read. It's 2 pi 50. Whoops, that's messed up. 50. So 2 pi times 50 times 30.37. Really? What am I doing wrong? Oh, because I didn't divide by 50. Oops. You're both right. 1.05 times 10 to the negative 4. That's right. Yep. I just did not divide the 50. I don't know why. Okay, so the answer is 1.05 times 10 to the negative 4. Or something like 105 microfarads, right? That would be 105 microfarad. Okay, any questions? You have at least one homework problem that's like this. Very, very similar. I think that the homework in the lab manual, I might ask about an inductor. I don't know. But either way, there we go. Oh, that's not it. There's a part C too. What power will be drawn from the supply line? What power will then be drawn from the supply line? Well, we've got this new capacitance, right? And we've got a new power factor. We probably also have a new RMS current too. Something that's not going to change though is the 50 hertz right here. Or sorry, well, that's obviously not going to change. The 120 volts, I believe, is what's not going to change. So what we'll need to do now is if we want to find the power, we need to know what IRMS is now. So to find IRMS, what we'll need to use is the fact that VRMS is equal to IRMS times Z. But if cosine phi is equal to 0, as we said above, Z is equal to R. So then VRMS now is just going to be equal to the RMS current. We're at like this. VRMS divided by R is going to equal IRMS. The resistance of our circuit's not going to change. It's still going to be this quantity right here. So we take our 50 volt line, divide by 30.37 ohms. And get 1.65 amps. And they plug it into this equation, and we'll have 1.65 amps multiplied by VRMS, which was 50. Wait a minute, it wasn't 50, was it? That was the frequency. It was 120. Sorry about that. It should be 120. And these are all wrong now. .95, yeah. Oops. And then we plug that in here for the current, multiplied by 120 volts. Now before it was 220, so now it's going to be quite a bit bigger. It's going to be 474. So in a way, this shows you something about how you basically kind of increased the efficiency of the output power in your circuit just by adding a capacitor into the circuit that kind of balanced out the fluctuations and thereby kind of increases the overall effect. So it's a way of making your circuit. I think the word that Mr. Meowers used last night was more efficient. More efficient. Because in both cases, there's the same kind of input voltage, but you're getting kind of more power out. Did you guys get the same answer, by the way? 120 was just the value given in the problem. 120 volts. Any other questions? Okay. We have a few minutes left, so let's talk about transformers. These are relatively straightforward in terms of like just getting through what they are. So here's an example of one. This is kind of like an ideal transformer. So a transformer is a device that basically can step current up or down, or voltages up or down. And the way that they work is through Faraday's law. So what you have is you have two windings of coils. On the left-hand side, you have some kind of source of alternating current. And on the right-hand side, you have basically just, in this case, it's just connected to a resistor. But this is, the way you can think about it is that like this is power coming in from the telephone company or from the power company. So this is like a power line. And then this would basically go off to a home. And these are usually, upload the diagram, this diagram here. Sure. Okay. And then, all right, so the idea is that you have some kind of source of alternating current. It could be coming in from a power line. It's alternating back and forth like this. And the thing that's different from the left side to the right side is that the number of turns of coil that are wrapping around here are different. So on the left, it looks like there's like 2 turns of coils that are wrapped around this core. This is an iron core designed to kind of enhance magnetic flux and to control field lines. On the right-hand side, you have more turns. And the way this ends up working is that we're basically going to kind of prove that the ratio of the voltages, kind of the input voltage, so to speak, to the output voltage, is going to be equal to the ratio of the number of turns. So basically what you can do here is you can start with kind of a smaller voltage over here on the left, and you can step it up into a bigger voltage on the right, or vice versa if you want to. And to understand how these work, they basically work off of Faraday's law. And the idea is that you're going to have an EMF that's induced in coil 2, and it's going to be equal to, according to Faraday's law, the number of turns into in the coil, multiplied by the time rate of change of the flux through the coil. The placement of the iron core here makes it so the flux that's flowing is going to be the same through each of these, with the only difference being this. There's also going to be an EMF that's coming from our source here, and an EMF that's induced in the first coil here as well, that's going to be equal to this. And what we do is we basically just equate the d phi dt terms here. So we end up getting basically that epsilon 2 over n2 is equal to, it's like EMF 2, EMF 1 divided by n1. And then we basically just say, well, those are going to be related to the voltages. So then we kind of rewrite them like this. We end up getting that E2 over E1 is equal to N2 over N1. And then we just relate these to voltages here, because these EMFs are also voltages, right? So you get this relationship right here. So as an example of how this is used, when you have power that's coming from power lines, that power has to travel long distances to get to your home, and depending on the amount of current that's flowing in the circuit, yeah, it relies off magnetic flux, absolutely. It also shows you, keep in mind, by the way, it relies on flux, but more specifically changing flux, and the fact that there's a alternating current in the wire on the left is what induces that flux, right? This really wouldn't work off of DC circuits. This is one of the main reasons why we don't use DC power. Instead, we use AC power. So the idea is this. You could have some kind of power station, like a place that, you know, let's say power plant, let's say. That power plant is gonna produce power. It's gonna send it out to some kind of substation that's in your area. And that power is then eventually gonna come to your home. Right? And there's a fundamental problem in doing this, that the power from the power plant needs to be sent to the substation, which then needs to be sent to your home, right? And these things may be very far apart from each other. So the power plant could be a few miles, it could be hundreds of miles away from your home. The substation maybe is only, you know, maybe you have one every block, or maybe there's one every neighborhood or something like that. But again, it needs to get to your home, right? And since we're going to send this power along wires, and those wires are not superconductors, there's going to be some kind of losses due to friction, basically losses due to resistance, right? And so you want to kind of minimize those losses as much as possible. So what you do is you send these this power, basically, with low current and high voltage. Now, you can look up what some of these values are, but coming out of the power plant, the voltage that you're sending could be as high as maybe like 100,000 volts. And then when it gets to the substation, there's a transformer here, which could step it down to maybe like 10,000 volts, right? And then there's another transformer at your home, another transformer right here that before it gets into your home, this transformer is going to be the ones that you can see on top of like power poles. Sometimes in the summertime they get really hot due to the fluctuations of these currents, and they can explode basically. But this final one is going to make sure that when it actually enters your home, it comes in at 110 volts, right? And it all just operates off of numbers of turns of coils, basically, right? So for example here, if this was our V1 and we wanted to get a V2 right here, we could figure out what the ratio of the coils needs to be, right? Because V2 over V1 would be 110 divided by 10,000. Okay, and so one simple answer would be, as long as the number of coils in 2 was 110 and the number of coils of N1 was 10,000, then you'd get what you want, right? But you can simplify that a little bit here, and we could have 110 over, what is this? So you'd have a ratio of 0.011, which would be like 90.9 to 1, something like 91 to 1. So this ends up reducing down to about 1 over 91. This is all talking about the way that like an ideal transformer works, as we often do in these books. And I know at the school we have transformers that we can like play with and you can measure voltages on. It never ends up being 100% like efficient, but so there's some kind of loss of efficiency as well. But this is kind of the basic idea of it. So that's a transformer we use to save money. Do I know how they separate dual or three-phase AC into single phase by any chance? So this would be like 3 different sources of alternating current that are all out of phase with each other. Is that what you're talking about? When you say single phase, they basically are taking those 3 different phases and kind of merging them into one. You're not saying to get the 3 different phases and get them into DC, are you? You're saying how to take the 3-phase AC into a single phase. Maybe they're cutting off 2 of those 3 phases. Well, I mean, I will say, depending on what the frequencies are, the frequency differences between the phases that you're describing, I would assume that you probably could amplify one of them pretty easily by kind of doing what we've described here, like using filters, basically. You believe power is sent over power lines as 3 phases, but to single... Yeah, that sounds correct to me. It's sent over lines as 3 phases, but sent to home as a single phase, and to industrial as T3 phase. Okay. I don't. That's something that sounds really familiar to me, but I don't immediately know exactly much about it. So maybe it's something we can talk about next time. If you want to read more about it, or I can try to read more about it. 3-phase AC. I'll try to remember that and see if I can learn something about it. It's interesting. It sounds right too that it's sent through different phases through the lines. Well, that's the end for tonight. I'll stick around if anyone has any questions, but that's that. Hopefully this problem up here that we did is helpful to you in doing some of the lab manual problems. Okay. Thanks, everyone.